Welcome back to the lecture series in animal physiology. So, we are in section 4, which pertains to the circulation and cardiovascular physiology. So, in section 4 we have dedicated 3 lectures, and out of 3 lectures we are done with the first lecture. In the first lecture we talked about the anatomical features of the arteries, veins, capillaries, arterioles, venules, and the zone of exchange of these materials by which the cells are supplied with the nutrients and the gaseous exchange and everything. So, now in this section what we will be doing, we will move on to the cardiovascular physiology of it. So, we have already talked about the heart physiology, how the heart is pumping, but then how the network of vessels carrying the blood all over our body is being governed. So, what are the governing dynamics which are regulating that flow? We will be discussing that. So, in this section, so what I will do, I will first of all draw the outline of the forces where it is involved, and in that process we will move on to enumerate. So, it will be much of slightly more informative than previous ones. Here you have to kind of gather certain informations and analyze them. So, it will be much of once the informations are there, you need to analyze them and then you have to put them in perspective. So, let us start with the broad outline of where all the checkpoints are and where we really need to put our maximum understanding in figuring out the dynamics of this network. Okay. So, let us start with the section 4. Section 4, the circulation and cardiovascular physiology. So, this is the second lecture. So, from here we move on to, let us see what are the control units. So, this will be a diagrammatic schematic view of it, where all we are having the control. So, we talked about the cardiac output while we were talking about the heart. Okay. So, this is very important, cardiac output. This is first thing, the cardiac output is being generated by the heart. Okay. And that leads to the arterial blood pressure, which is the actual blood pressure, arterial blood pressure encompasses something called, and we will come to that, peripheral resistance, because as you remember in the last class I was telling you, because of the reduction in the size of the, or the reduction in the diameter of the vessels. So, for example, arteries are of huge diameter, then you are moving to the arterioles, and okay, let us start with the elastic arteries, then moving into the muscular arteries, then you are moving to the arterioles, and then you are moving to the capillaries. So, there is a continuous decline in the diameter. As the diameter keeps on decreasing, the pressure changes. Okay. So, you are reducing the diameter, so the radius is continuously varying. So, that reduction in radius leads to a resistance in the flow of the blood, and we will be talking about that, and those resistance which are generated by the arterioles and the capillaries falls under the peripheral resistance, and from there the blood moves on to the capillaries, which are exceptionally perforated vessels, as we have discussed in the last class, and this is the zone where the maximum gas and fluid exchange taking place, okay, with the interstitial fluid. And then from there it leads to the venous pressure or the pressure in the vein, and this whole process is being controlled at every level by the nervous system and the endocrine system. Nervous system and endocrine system. So, what essentially we will do is, today we will talk about the cardiovascular physiology at 2 levels. The first level we will be carrying is at the level of arterial blood pressure. This is a very critical point what we are going to cover here. Second thing we will be talking in the next lecture, we will be talking about the capillaries and the interstitial fluid exchange. Okay. So, where basically all the capillary exchange is taking place. Then what we will do at this stage, we will stop. with this section, but we will partly come back to this section again while we will be dealing, once we are done with the endocrine system and the nervous system, or while we will be doing the endocrine system, we will talk about the endocrine control and we will talk about the nervous control. But at this stage, since I have not taught you the nervous control or the endocrine control, so I will not deal with it, because that will not make sense to you people, because without getting a fair idea about the molecules which are generated by the nervous system or by the endocrine system, it will not make sense. Okay. So, again to summarize, what we will be dealing with, we will be dealing with the arterial blood pressure and we will be dealing with the capillary exchange, and then we will be dealing with the fetal circulation, and in between we will talk about the blood pressure, pulse and all those different parameters, which are very essential for you people to know in day to day life. So, always remember that by the end of the course, I expect that you people should know, whenever you go and talk to a doctor, what the doctor is telling, or you see a prescription somewhere, a doctor tells you this is your pulse, this is your blood pressure, these are the problems, this is arteriosclerosis, or this is your ECG, this is your EKG. You should have some degree of basic understanding what that means, and that is the whole purpose of this course. It is very practically oriented, that you should be able to figure out these things. Okay. So, let us move on to the arterial blood pressure. Okay. In order to explain the arterial blood pressure, what I will do, as I told you, this will be slightly more informative section. So, I will acquaint you with some of the basic definitions, and these definitions are very, very important, and then we will draw up the story. The first definition you have to understand is the blood flow. Blood flow is essentially, so I will write it down so that you guys start analyzing these definitions. The volume of blood flowing per unit time through a vessel or a integration of several vessels, as long as you know the total surface area and the volume. Okay. And total blood flow is essentially equals to the cardiac output, and cardiac output we have already done in the previous class. This is the first definition I expect you guys to know. The second definition is what is blood pressure. So, blood pressure is essentially the hydrostatic pressure in the arterial system that pushes blood through the capillaries. Okay. That pushes blood through the capillaries. So, one term which may confuse you is what is hydrostatic pressure. So, what we will do, let us understand what is hydrostatic pressure. Okay. Using certain very simple diagrams that will help you to understand what is hydrostatic pressure. One second. Okay. We have talked about the osmotic pressure in the membrane section, membrane physiology. So, here we will talk about how we actually measure the osmotic pressure. Okay. So, let us think of a situation, let us think of a U tube like this. Okay. This is a U tube, and at the bottom of the U tube you have a membrane like this, which I am indicating in black. Okay. This membrane only allows, this membrane, mark my word very carefully, this membrane only allows the water molecules to pass through it. Okay. It does not allow any other molecules, which I will be drawing, any other solute molecules to pass through it. So, let us add up a whole range of solute molecules. These are greens are solute molecules. Okay. This could be sugar, this could be something else, or dextrose, or XYZ, it could be anything and everything. Okay. But mind it, these molecules cannot pass through the semi permeable membrane. Okay. So, let us mark this side, my left side as A and this part of the tube as B. Okay. Now, what I do? I add water to both sides, and mind it, this will allow water molecules to pass through them. So, how about we show the water also in terms of the molecules that will make life easier for you guys to understand. Okay. These are the water molecules I am adding. Okay. These all the green, all the blues are the water molecules. How about I take a slightly bigger that will make life easier. Okay. So, this is the first case scenario. Now, what will happen if we allow this to equilibrate for a while? What will you see is that, so if you look at it very carefully into this picture, you will see the solid particles are more on one side as compared to the other side. So, in other words, solute particles are more in the B as compared to the A, much more. Okay. If you look at it, carefully, or I can add few more. So, these solute particles will try to draw as much as water possible towards B in order to equilibrate this situation. Okay. So, what eventually will happen in order to reach the dynamic equilibrium, this is what is going to happen. The same tube, I am just using a thicker point. Okay. Let me get back to, okay, fine. So, what will happen is that essentially what you will see is, and here is your semi permeable membrane. Okay. This is your side A, and this is side B. So, eventually what you will see is that there are more water molecule on this side as compared to the water molecule on the other side, because of the fact that these are the water molecules, and if I had to put the there is a slight disturbance. Okay, let us come back to the lecture. Okay, talking about the hydrostatic pressure. Okay, this is what we are going to discuss, hydrostatic pressure. So, I told you the solute concentration on the side A, if this is A and this is B, the solute concentration on the side of B is more, and this is the semi permeable membrane. This is the which only allows water to pass, semi permeable membrane allows water molecules to pass, and I told you that since on the side of B the solute concentration is higher, so automatically, so now I am showing the solute by red actually. Solute is higher, and here is the by blue I am showing the water molecule. There will be a shift of lot of water molecules on the side B, and so just again to show you section B. So, this is number of solute molecules is extremely high as compared to the solute molecules on one side. So, this is side B, side A, side B. So, number of solute molecules in side B is exceptionally high as compared to solute as compared to the solute concentration on side A. Now, what will happen is that side B will drag a lot of water molecules towards it because of the osmotic pressure. So, now in order to equilibrate in terms of the potential difference, if I want to get back to a situation like this again, like where if I am just showing drawing a smaller tube, if I want to show something like this on both sides is equal, I had to put certain amount of pressure from here on this. This pressure has to be put in order to bring it back to equal potential difference on both sides, which will be against the solute gradient and everything. Okay. So, in order to do that, the amount of pressure what I have to put on the side B is equivalent and opposite to the osmotic pressure, and that pressure is called the hydrostatic pressure. Okay. So, this is the hydrostatic pressure for your understanding. So, the amount of equal and opposite pressure to the osmotic pressure which has to be given in order to bring it back at the same potential difference. So, something like this from where we started, which I showed you. So, these are the three cases in order to explain the hydrostatic pressure. Okay. From here we move on to the next slide, which is our circulatory pressure. Circulatory pressure. What is circulatory pressure? The pressure difference between, so this is very important, the pressure difference between the base of iota and base of the ascending iota and the entrance to the right atrium. Entrance to the right atrium. Circulatory pressure is the pressure difference between the base of the ascending iota and the entrance to the right atrium. So, in other words, right atrium is the one which is receiving all the impure blood or the deoxygenated blood, and the ascending part of the iota is the one which is the maximum pressure from the left ventricle. Okay. From the left ventricle, which is circulated all over the body. That pressure as compared to the pressure with which the blood is coming back to the heart into the right atrium, that pressure difference is the circulatory pressure. Okay. Now, what is the technical definition of hydrostatic pressure? I have already explained you the hydrostatic pressure, I am just giving you a definition. Hydrostatic pressure. Hydrostatic pressure is a pressure exerted by a liquid in response to an applied force. Okay. Next, we will go to what is peripheral resistance. As I told you, there are a whole bunch of definitions which I have to kind of appreciate and realize. Peripheral resistance, the resistance of the arterial system affected by such factor as vascular resistance, viscosity and turbulence. So, these are the resistance which are offered due to vascular resistance, viscosity and turbulence falls under the peripheral resistance. Then we move on to what is basically the resistance is in terms of blood flow is anything resistance to blood flow is anything which is opposing if this is the blood flow anything which is opposing the blood flow or kind of that is called the resistance to the blood flow. And we talk about the total peripheral resistance. Total peripheral resistance is the resistance of the entire cardiovascular system. The resistance of the entire cardiovascular system is called the total peripheral resistance. Then there is another term which I just mentioned is called turbulence. What is turbulence? Turbulence is a resistance which is generated, a resistance due to the irregular swirling movement of blood at high flow rates or exposure to irregular surfaces. Something like this. Say for example, this is the blood vessel and here you have the surface becomes like this. So, what is happening? The blood which is coming like this is kind of start moving like this here, it's kind of create eddies out here. These are the turbulent nature of the flows. Okay? This is the basic example of a turbulence. The same thing which happens while you are in the airplane and we get trapped in a air pocket. Okay? Then there is something called a vascular resistance. What is vascular resistance? Vascular resistance is a resistance due to friction within a blood vessel, a resistance due to friction within a blood vessel, primarily between the blood and the vessel walls. Increase with, and mind it, let me continue on the next slide. And this vascular resistance increases with increase length of the vessel, increase length of the vessel, this is important, and this decreases with the increase in diameter of the vessel. So, if you realize this, this is exactly what is the situation in the veins, where in the veins the diameter of the vessel is fairly high as compared to the arteries. So, as the diameter of the vessel increases, the vascular resistance decreases. So, it moves without much resistance likewise. Okay? So, this is, and we will come to all the mathematical derivation of it, and then we move on to the venous pressure. We talk about the arterial pressure, now we are talking about the venous pressure or the hydrostatic pressure in the venous system. That is talking about the venous pressure. Then we talk about the viscosity, the end. We have mentioned this. So, viscosity is essentially, say for example, you take water, you try to flow water on a surface, it fairly flows without much problem, but you take some kind of syrup, okay, some kind of sugar syrup or some other syrupy fluid which is much more, have a lot of carbohydrates and sucrose in it, and try to flow it, something like a marmalade or jelly or something, that won't flow because it is exceptionally viscous fluid. In other words, the interaction, the resistance which is created. So, there are several ways of resistance. So, water is flowing on a surface, okay, the water is flowing on a surface. So, the surface is kind of, surface is rough. So, automatically it faces a resistance. Okay. There is another form of resistance. Say for example, the surface is same, but you are trying to flow water and you are comparing this while flowing some kind of syrup. So, that is a situation where you will see syrup won't flow faster. Syrup won't flow faster because there is a friction which is generated because of the interaction of the molecules within the syrup. Okay. So, it is something like a resistance to flow due to interaction among molecules within a fluid. This is very important. This is the key point. This is the resistance which is created because of the interaction between the molecules within the fluid. Now, if we have to draw the relationship among these terms, let us put all the relationship between the terms which I have just now written. Okay, let us talk about the relationship. So, the flow is proportional to, where F stands for the flow, okay. Flow is proportional to change in pressure, delta P is the change in pressure, this is the first relation. So, there will be more flow if the pressure gradient is more. So, if something like that, here they have P1, here you have P2 and P1 is far more greater than P2, then there will be more flow. Flow is inversely proportional to resistance. If there is more resistance, there will be less flow. If there is less resistance, there will be more flow. Third relation, flow is, if I add these two equations, flow is directly proportional to change in pressure and inversely proportional to resistance. This is coming from equation 1 and equation 2. Okay. Moving on to the fourth relationship, flow is directly proportional to blood pressure. Of course, we have to explain what is blood pressure. Blood pressure and inversely proportional to peripheral resistance. This is the fourth relationship. The fifth relationship is R, which is the resistance to flow, resistance to flow of blood, is inversely proportional to 1 by small r to the power 4, where small r is the vessel radius. So, in other words, resistance is inversely proportional to the 4th power of vessel radius, 4th power of vessel radius. This you can always plug in the values of the veins and the arteries, especially the diameters or internal diameter what I have given you. You just make it half and get the radius, and you plug in the values, and you will see how the resistance varies in terms of what is experienced by the blood in the artery vessels as compared to the one which is experienced in the venous vessels. Okay. So, let us move on to the next slide from here, which I will be talking about. let us diagrammatically show how these values are changing. Okay. So, what I will do now, I will divide the page into all the vessels. Okay, let me do it like this, 1, 2, 3, and I'll just give me what I wanted to show you here, 1, 2, 3, 4, 5, 6, 7. Okay. Now, the first thing what we will be talking about, the vascular diameter and how that is changing. Okay. So, this section is your elastic artery, I am just putting it EA because there is space constraint here, muscular artery, and this is arterioles, and this is capillaries, this is venules, this is the veins, and this is vena cava. Okay. So, now the first parameter we will be dealing here is the vascular diameter. Although we have done it, now I am just kind of putting it in perspective. 1, 2, and 3. This is in centimeters. Okay. So, the way the vascular diameter varies is something like this. So, vascular diameter from here, let me put another, okay, goes down, down, at the arterioles it's come down, with the capillaries it is the least, and from here it increases with the venules, veins, and the vena cava high. So, this is how the vascular diameter changes. It is the least in the capillary section. So, what I will do, like, I will just keep on, this is the baseline where the maximum exchange is taking place. Okay, the vascular diameter decreases. Now, we will talk about the total cross sectional area in terms of the vessel. Total cross sectional area in centimeter square. Okay. How that is varying. So, you have 1000, 2000, 3000, 4000, and 5000. Okay. Now, the way it varies is, let me use a different color here. Okay. The way it varies is something like this. It moves like this, this increases, and then it becomes highest out here, and then it falls down like this. So, if you look at it, the total cross sectional area is highest in the capillaries. So, actually this graph should shift slightly. Sorry, let me redraw the graph for you guys. It's more like this. Okay. This is how the total cross sectional area changes. Okay. The next we will talk about the pressure in these vessels in terms of, let us put this 100 millimeter mercury, this is the millimeter mercury. Okay. The way the pressure changes is that, so it is the highest at the elastic or the iota, and then it goes down, 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 and it becomes even lower out here on, and then lower, 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 lower. So, if you look at it, so here the capillary pressure is sitting. Okay. So, I am keeping this as constant reference. Now, on top of this, if you wanted to check what is the velocity of the blood. So, let me move on to the next slide. Again, let us draw those lines, that will be helpful to understand it. 1, 2, 3, 4, 5, 6, 7. Okay. Now, So, in terms of the velocity, if I have to measure, which is in terms of centimeter per second. So, the velocity profile, and this is elastic artery again, this is muscular artery MA, this is arterioles, this is capillaries, this is venules, this is veins, this is vena cava, VC, okay. So, the maximum is approximately is the 35, if I put it in, and this is the baseline. So, it shifts like this. So, maximum out here and then it goes down, 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 it is the lowest out here and then there is a slight increase likewise. This is where in the capillaries the pressure looks like. So, these are the changes of the 4 parameters, which includes vascular diameter, cross sectional area, average blood pressure and your speed or the velocity with which the blood is flowing. Okay. Next, what we will do, we will move on to what is the arterial blood pressure and how it looks like. This is very interesting to realize. The arterial blood pressure is never constant, because there is a continuously. So, it is something like this. If I had to give a definition of arterial blood pressure, and then I will diagrammatically show you this. Okay? Arterial blood pressure. So, arterial blood pressure is important because it maintains the blood flow through the capillary beds, okay? And how it maintains, okay? But we will be coming to that. Maintains the blood flow through the capillary beds. Okay. And to do so, it must be enough. To do so, it must be greater than or more than the peripheral resistance. It has to be more, otherwise the arterial blood pressure cannot make blood flow through the capillaries. Okay. So, arterial, I am just putting it at ABP as the arterial blood pressure is not stable and it is not fixed, or rather that is not the right way to put it, it is actually it varies within a range. So, just a practical situation. So, whenever, now let me come back to give you a practical idea what really blood pressure is. Whenever we report a blood pressure, we say higher pressure and lower pressure, we say 120/80, or we say 150/90. Likewise, you always see two numbers. Why is it so? Why it is a two number? This is something what you have to realize. So, practically it is very simple. If you remember, so before I give you the real definition, you have to. So, if you remember when while I was telling you that blood from the left ventricle is pumped through the aorta, the oxygenated blood to the whole body, and the pressure is maximum when it leaves the artery, and especially when the semilunar valve closes and it won't allow the backflow of the blood. So, at this stage, so when this blood moves there, the left ventricle goes into a diastole. It is in a relaxed phase and it goes into the systolic phase. So, there are two shifts, once it is in a relaxation phase, once it is in a contraction phase. Contraction phase is the systolic phase, when there is a maximum pressure on it, that we call as the blood pressure measured at that time on the arteries is called higher side of the blood pressure, and then it goes down because of the diastolic pressure when the left ventricle is relaxed state, that is called the lower blood pressure. Based on that, we will put the definition now in perspective. So, that is the arterial blood pressure is not stable. That is why it varies in the, or is not fixed or is not stable. So, it increases during ventricular systole and falls at ventricular diastole, because this is the relaxed phase and this is the contraction phase. Okay. So, the peak, so what we do essentially is that the peak blood pressure measured during ventricular systole is called systolic pressure. Systolic pressure, or the upper regime of the blood pressure. So, when you talk about 120 by 80, so this is this. The systolic pressure is that 120 is the systolic pressure, and is minimum during ventricular diastole. So, 120 by 80, what you see, this is 80 is the one when is the diastole taking place. So, it could be 120 to 80, it could be 110 to 75. So, these are all the diastolic regime. So, if this is so, then what the way it is being reported, so it is why it is called average blood pressure or average arterial blood pressure, sorry, average arterial blood pressure. So, this is basically the way it is good, or it is also called mean arterial pressure is equal to diastolic pressure plus pulse pressure divided by 3. Pulse pressure is the difference between the diastolic pressure and the systolic pressure. Okay. So, for example, you have somebody has say 120/90. The systolic pressure is 120 and 90 is the diastolic pressure. So, what you do, you plug in the formula, mean arterial pressure will be 90 is the diastolic pressure plus, so the pulse pressure here is 120 minus 90, which is 120 minus 90, which is 30 divided by 3. So, that becomes 30 divided by 3, that becomes 10. So, the mean arterial pressure of this individual is 100 millimeter mercury. Okay. So, this is how the blood pressure is being reported. So, now diagrammatically I have to show you this. Again I will follow the same diagram that will help you. 1, 2, 3, 4, 5, 6, 7. So, you have the aorta here, elastic artery, muscular artery, arterioles, and you have the capillaries. Okay. Capillaries, venules, veins, and vena cava. Okay. These are all the vessels in a sequence where it comes back. And here you are measuring the okay. So, the way it varies, this is 180 is the top line and the y axis, and here we have 80 this line, here 100 out here, and likewise you can go down to 0 and likewise. So, this is millimeter mercury. The way it varies is something like this out here. So, it varies like this. So, this is what happens. So, if I mark them with different colors now, systolic pressure, systolic pressure, systolic, systole, 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 systole. Now, the diastole are in black, diastole, 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 diastole. Now, what I do is that I draw an average between these two, and which is this line. I am drawing the other additional line. Let me draw it with slightly okay. This is the average line what I am drawing. This is your one second. So, this is your average blood pressure. This is very, very important for you to understand. What I was trying to verbally tell you, this is how the pictorially it looks like. This is the average blood pressure, what you are actually what we measure. Okay. From here we move on to another very interesting term which is very important for us to understand is one more thing here, just for those of you who suffer from hypertension or hypotension. Hypertension is a situation when, from this diagram itself I can tell you what that meant is, when this value from 120 it exceeds up. Okay. So, your blood is really moving really fast. So, there is always a chance when they say you do not get very angry, you are in a hypertension mode. What happens is that blood is moving really fast because pressure is very high. Under that situation there is always a chance of a hemorrhage. Vice versa, if you are a low pressure person, you are sinking, it is here, the pressure goes down. So, the blood is moving very sluggishly out there into your blood vessels. So, these are the two extreme situations, hypertension, and it is very interesting. I mean, the modern research is showing those who continuously take drugs on hypertension actually suffers from hypotension. You are taking drugs in order to bring down your movement of the blood along the vessels, and eventually you actually suffers from this kind of situation when you become a hypotensive after a point of time. Your body kind of gets used to with it and it just brings it down. So, these are some of the things which may help you to see certain physiological regime of certain drugs whenever we use them. Now, from here I will move on to one of the very interesting part which is called elastic rebound. What really elastic rebound is? So, let me try to explain it first, and before I draw it or give you a basic definition. So, one of the essential point is that the blood, the oxygenated blood from the left ventricle is pumped all over the body. The pressure is very high at that point of time. So, now how that pressure is being sustained so that the blood flows through the capillaries. But if you look back and if you go back into the slides while I was showing you diagrammatically, if you look at the velocity goes down in the capillaries. Look at this. Okay. Go back further. If you look at it, the pressure goes down in the capillaries. Okay. And yeah, I think these are good enough point to make my statement. So, if these pressures are going down in the capillaries, how it is being maintained out there. So, even that much pressure, how it is being maintained? Pressure at the aorta, there is no problem. That is being maintained by something called elastic rebound. What exactly happens is that whenever there is a systolic pressure, okay, systolic pressure, the aorta is kind of all kind of filled with blood, okay, because now blood is about to be pumped out, and as it does so, it accommodates a significant amount of blood into these vessels, and when it goes to the diastole, even the residual blood moves into the artery. It has a lot of elasticity to accommodate that additional amount of blood. Now, it can accommodate, it is just like a pipe, okay, it can accommodate certain things, but then what I do, I close the source. So, say for example, from the top the blood is coming out into these vessels. If this is the vessel, okay, imagine this is the vessel. Now, it is coming out, but then it has a limit. It cannot really expand to beyond a point. So, then what I do, I close down, so it cannot bounce back. Okay, then it has to exert its pressure. So, back towards the heart it cannot, because it is being closed because the semilunar valve closes. And once the semilunar valve closes, the blood cannot flow back from the aorta to the heart. So, now it recoils back. Well, it recoils back, it generates a forward pressure, and that forward pressure is nothing but it is called elastic rebound, which is essential for the capillaries to function. Okay. So, let me just put it in terms of The definition, how that will look like: elastic rebound. Elastic rebound is essentially situation like this. Okay, there is an increase in systolic pressure climbs. Okay, first step leads to the arterial wall stretches. Okay, then this leads to allowing arterial system to accommodate some of the blood provided by ventricular systole. Okay. Next, let us continue. When diastole begins, the blood pressure falls. As I have already shown you in the graph, the arteries recoil. This is highlighting point. The arteries recoil when the diastole begins to their original dimension. Now, when it has to recoil back to its original dimension, the aortic semilunar, SL stand for semilunar valve, prevents backflow of blood to the heart. So, what are your options? So, arterial wall recoil pushes blood in forward direction towards capillaries, and this phenomena is called elastic rebound. And this elastic rebound is exceptionally important for you people to understand that this is the one which ensures that the blood moves, the pressure is maintained in the capillaries. And one more thing I will just add here is the pulse. A pulse is basically a rhythmic pressure oscillation that accompanies each heartbeat. Okay, the definition of the pulse is essential here. It is a pulse is a rhythmic pressure oscillation that accompanies each heartbeat. Okay, so this is, and I talked to you about the pulse pressure. So this is essentially is what you people needed to know about the cardiovascular physiology, and it is as you go through all the definitions and everything that will make more sense that how all these things are related. So what is left currently, when we started, I gave you a drawing saying that okay, that we will be talking about all the control units. So next, in the next class, what we will be doing, we will be talking about the capillary exchange, and we will talk about the fetal circulation. So that way we will conclude this section. Thank you.